welcome back. Today we're going to continue talking about a different way of addressing machine learning problems. We're going to take a more theoretical perspective and see what is the best learning that you could possibly do on a given problem or data set. And so to do this will require being a little bit more philosophical. What does it take to actually learn something? What does it mean to learn something? And to address that question, we're going to have to think about what are the things that we're learning? So we're learning some sort of classifier. What does that mean theoretically? And given some data set, what does it mean for a data set and a problem to be learnable? And hopefully, after we're done today, we'll have put in place a framework for reasoning about what it means to be able to learn something theoretically. So when can we take some data and learn about it? And so many of these insights that we'll get will be useful. They'll help us build better machine learning algorithms like support vector machines. And sometimes they won't be so useful. Sometimes you can still do a good job of learning something even when the theory says that it should be difficult. And sometimes the theory says that something should be easy when it actually isn't so easy, and it turns out to be more difficult. But it's very useful to know this theory because it does often provide good guidelines about when something can be learned or not. Okay, so to motivate this, let's say that we have someone who just moved to Colorado. Let's say that they're from California, and they have no idea what people mean in Colorado when people say that it's nice outside. And so this person from California has a perfect thermometer, but natives call 10 degrees Celsius or 50 degrees Fahrenheit nice. And the Californian has no idea what's going on. Okay, so in this case, each temperature is some observation, x, and there's a Coloradan concept of nice that takes input x, which is a temperature, and then says whether it's nice or it's not nice. And then a Californian wants to learn some model of niceness in the great state of Colorado that is close to the native concept of niceness. Okay, any questions on the setup?
C of x is the true concept.
Exactly.
We want to get as close as possible, right?
Exactly. And this should remind you of some of the things that we've been talking about in this machine learning class. You can think about C of x as sort of your golden true classifier, and h of x is the thing that you're learning from data.
But C of x is unknown, right?
It's unknown, but it exists.
Okay.
And what we want to do is we want to have low error, and we want to have low error on unseen examples. And so we're going to call this generalization error. We have some examples that come from our universe of data, and we want our learned hypothesis to be as close to the true answer as much as possible. So we want this generalization error to be as low as possible. And so we'll rewrite this using an indicator function. And this is 1 whenever the argument is true and 0 otherwise. So this is just counting up how many times this doesn't match, and then using the expectation to turn that into something that looks like an error. And we want this to be as low as possible. Okay, any questions on this notation?
Well, the inequality here, like h of x is not equal to c of x.
Mm-hmm.
I mean, you must have some kind of criteria to define the inequality. I mean, you said...
So these are just binary variables, and so nice and not nice. And so are they the same or not?
Oh, I see.
So this is discrete classification, so there are only 2 answers. And when we talk about this theory, we're going to be talking about discrete things that we're learning.
Okay.
Yeah, but you're absolutely right. If we were doing something like regression, you can't have absolute equality of real numbers. That wouldn't make sense. So these are binary outcomes.
Okay.
Good point. So notice that this is the distribution over the universe of data, not an actual data set. Okay, so the Californian does learning. And so the Californian gets some examples, and we'll say that they get in examples. This is their training set, as it were. And so some of these will be positive, and some of these will be negative. So nice days on for some temperatures and not nice days for other temperatures. And so how might you build a concept class for niceness?
You just look at those positive, the positive examples, and you circle this area.
Yeah, so we can make a range going from the lowest nice temperature to the highest nice temperature, and then that becomes our concept class. So there are other ways you could do it. Let's just say that this is the algorithm that the Californian applies, given a bunch of observations. Okay? But this could be wrong. So let's now draw. So this was what the Californian learned, but the truth could be bigger. There could be some error. So we know that it's going to be less than this guy, but it could just be epsilon less than that. So the true concept class could be over here. And maybe the true concept class is a little bit further to the right of 30. But it could be anywhere in between these two examples where it changes for the first time. And so we'll denote these two gaps as delta CA, going from here to here, and delta BD. Okay, so this is the gap between what we learned, h of x, and the true concept class. Okay, so now we can finally define what it means to be learnable, and we'll call this PAC Learnability. We'll explain what PAC is in a little bit more after we've gone through this definition. So, a concept is PAC learnable if there exists some algorithm and a polynomial function such that for any epsilon and delta, for all of your data and for all concept classes, the generalization error is less than epsilon with probability greater than or equal to 1 minus delta. Okay, so let's look at what we have here. So here we have S, which is our sample drawn from some data distribution D, and we have M samples of that. And we have some hypothesis that we learn as a function of that sample. We have our generalization error that is less than our bound on the generalization error, and the probability of our error is delta. So we want this to be relatively small so that the probability of having low error is good. Okay, so now let's take a look at how bad things can happen. And so we can have bad generalization error if we don't see anything in delta CA or delta BD. And so if these regions are large, then we can have a big error. And so the only way that that could happen is if none of our training points landed in this region. And so this is basically saying that so let's just focus on delta CA for the moment, that we have no points landing, so x1 didn't land in there, up to xm, none of them landed in here, so taking all of those events together, ANDing them together, that's just a product of probabilities. And we want the probability of the point landing there to be less than some value, and we actually want that to be less than epsilon, and we want that to be true for all of our m points. So this should be confusing. We haven't gotten there yet, but does everything to the left make sense?
Well, why is it a bad event if no training point in the delta region? I mean, if a point lands in the delta region, does it mean that this is wrong?
Right. So it's good in training time if a point lands in that region, because then we know where we have a better idea of where to put our concept class. It's bad at testing time if a point lands in that region, because we will get that wrong.
Oh, so it's better for us to decide the boundary.
Exactly. So this is the critical region where we can make mistakes. And so we want training points to land in that region. And we can get an error if at training time this region is very large because no training points landed in there.
Okay.
Okay. All right. So, and we want it to be true that to minimize the probability of a bad thing happening, the only way that could happen is that no point in the training set, any of our m points, landed in that region. So we want to bound that probability, and this is sort of a messy algebraic term, so we'll apply a trick. The reason that this is a product is that all of these are independent, and so now we'll use this trick. If you have 1 plus x, that's always going to be less than e to the x. And so we can just replace 1 minus epsilon times, 1 minus epsilon, we'll replace that with e to the m. Okay. So we want the generalization to be less than delta, so we'll solve for m. So m is the number of samples we need in order to get a good generalization error. So we want our generalization error to be greater than or equal to epsilon with probability less than or equal to 1 minus delta. And so we're just going to take this over here and substitute it in here. So why is there a 2 there?
You mean in the equality 6?
Yes, that's right. So let's go back to the picture.
Because you have 2 regions?
Yeah, exactly. So there are 2 places you could make a mistake. This side, this region here, or this region here. Okay, so this analysis is symmetrical for both delta CA and delta BD. You can have mistakes on either side, so that's why the 2 is there. And so delta corresponds to the probability of a bad hypothesis. And so now what we can do is we can take the log of both sides, And so that gets rid of the e over here. And then we also divide by the 2. And then we'll divide by negative m, and that flips the inequality. So this gives us the number of training points we need if we want to have our generalization error to be less than epsilon. Okay, so now we have an answer. So if you can plug in the numbers, and if you're Californian, these are the number of days you need to observe in Colorado to figure out what niceness is to some epsilon with probability delta. Okay.
Oh, well, I have a question.
Yeah. Mm-hmm.
The R of H is the generalization error, right?
Mm-hmm.
But when you plug in the, when you expand the equality, you use m samples.
Mm-hmm.
And I remember that you said R of H is a kind of universal error. So why can you just put this m samples why can you just use this m samples to represent the generalization error?
So that's a good question. So many slides ago, we talked about how R is supposed to represent not a data set, but how well you do on the whole universe of observations. Mm-hmm. And so the reason that we can do that is this. So this is where we are using the fact that our samples came from the true data distribution. So our samples come from what we believe is the true data distribution. And if our data distribution doesn't have a lot of points in our dangerous region, we won't see many samples there. So this is how we're using the probability of samples landing in a particular region. And so this, our samples are coming from D. So X comes from D. And so we're using the probability of samples from D landing in a particular region, and we're using our data that we took as our training set to estimate that probability. And so the way this works is that if we don't see samples in this region, then the data distribution doesn't put a lot of points there. And so no matter what the data distribution is, we have good probability of learning our class.
Okay.
Okay, so now let's go back to what this is called. So we'll go back to the definition. So why is this called probabilistically approximately correct? Yeah, go ahead.
Because you have a probability here. You want to guarantee the error with probability.
Right. So let's the probabilistically. So this corresponds to this bit here. So probabilistically is that we have some delta with which we want to bound the probability of being wrong. And so we're not saying that we'll always be right, but with high probability we will learn a good concept. And so approximately comes from the epsilon, that we aren't requiring ourselves to be perfect. We're going to be less than some error. So that, and then correct is coming from the generalization error. So if the generalization error then is low, then we're correct. Okay, all right. So now we can talk about more general cases. And so next time we'll talk about when specific problems are learnable, But for the moment, let's talk about something a little bit more general. We'll now prove that finite hypothesis spaces are learnable if they're also consistent with training data. So this will have a form very similar to what we saw before. If you have a hypothesis set H, which is a finite set of functions mapping from your input space to your label space, and you have some algorithm that for an IID sample returns a consistent hypothesis, that is, its empirical error is 0, then you can prove a PAC learnability for that concept. And so this has a very similar form to our bound for the California interval learning. And in the California interval learning example, we need a number of examples based on our error tolerance and the probability of getting that wrong from our data. This has a very similar term, so both of those are present, but then it also has some notion of the complexity of our hypothesis class. And this is implicitly in our California learning example because we had that 2 that represented some notion of the complexity of our hypothesis space, but here it's much more explicit. It's based on the size of the hypothesis set. Okay, so let's try to learn this. Okay, so we want to bound the probability that we have an individual hypothesis that's consistent and has error more than epsilon. Okay, so we want the probability that we're consistent with our training data, so that this statement corresponds to that, and our generalization error is greater than epsilon, and this is what we're going to try to bound. Okay so far?
Yes.
All right, so we're just going to expand this out. We're going to say that H1 is in our hypothesis set, and the empirical error is 0, and the generalization error is greater than epsilon, on out through all of our H's. Okay, so what we can do is we can then take the union bound, and so the union bound just says that if we have a bunch of ORs, we can add their probabilities together, and the probability of, if you sum the probabilities of the individual events, that's going to be greater than or equal to the probability of the union of those events. Okay? And then we can just apply the definition of conditional probability. So probability of A given B is equal to the probability of A and B divided by the probability of B. So that's just the definition of conditional probability. So this is the conditional probability down here. So that's going to be less than the joint because the joint needs to be divided by probability of B, and that's a number less than or equal to 1. Okay so far?
Yes.
All right. So this is the probability, and we want of something bad happening, and we want this to be small. Okay. So if the generalization error is less than epsilon, then we can bound the probability of no inconsistent points in our training set for a single hypothesis H. So here we have the sum H, and now we're just going to look at a single hypothesis. And so but this must be true for all of the hypotheses. So we can just multiply that by 8, since if it was true for any hypothesis, then we would have picked that instead. So all of these hypotheses must be bad, so we just multiply that by the number of hypotheses. And so this is a probability of the bad event that we don't want to have happen, delta. So what we can do is we'll apply the same exp trick that we did before. So 1 minus x can be replaced by e to the x. And then we'll take the log of both sides. So this should look very similar to what we did before in the California case. And then we'll use a little trick. So we'll write log of delta as -0 minus the negative log of delta. And so then you can factor the -1 out and turn log of 0 into, you can turn 0 into log of 1. And then you have this negative log, and then you can rewrite that as negative log of 1 over delta. So now we've moved this over to the other side. We've rewritten negative log of delta. Then we can divide by negative epsilon. And so now we've gotten the form that we wanted. So we have all of these hypotheses. All of them have had a generalization error of 0, but an empirical error of 0 and a generalization error greater than epsilon. We combine all of those together, and when we work through this, we now get the number of examples we need to bound our probability of a bad event happening. Okay, so let's inspect this a little bit more. So if you want to be more certain, either having a lower generalization error or a higher probability of being correct, you're going to need more data. And if you have a larger hypothesis set, you're going to need more data. So the more complex the hypothesis you're going to learn, the more data you need. Okay, so here's a scary question. What is the size of the hypothesis set for logistic regression?
Well, I think it's the different ways to classify the data.
Mm-hmm.
Like 2 up m?
So 2 to the m. So that would be a lot of different ways of classifying it, and so we'll see that it's a little bit more complicated than that. Another way, I like asking this question at this point because there are lots of different answers that people come up with. So this is one perfectly reasonable answer. Another answer that you might get is infinity. So someone might say that there are really infinitely many logistic regression classifiers because beta is a real vector of length equal to the number of features that you have. So there are an uncountably infinite number of possible betas. Each of those is a different classifier, right? So,
maybe 2 different kind of classifiers will get the same reason. Same result.
Aha, yeah. So that's a good point. And so I'm not going to answer this question now. This is something to think about. The reason that I mentioned this is that we're going to have more sophisticated ways of looking at the complexity of a classifier. And as we'll see in the next lecture, there are geometric arguments that you could make about the ways that you can divide points in some geometric space. Okay, so in class, we'll work through some more examples of PAC learnability. Make sure you come to class with your questions, and next time we'll see how we can deal with questions like what is the size of the hypothesis set for logistic regression. Okay, thanks. And